Okay, hello. Another day of very chunky internet. Oh, maybe I should get a Starlink terminal. But yeah, it's very tricky. Yeah, it keeps on going in the red, and it's very laggy from my preview on my phone. So we'll see how it goes. We'll see if we can go through chapter 10 at least, then maybe go into chapter 11, but I want to finish chapter 10. I have something to do this afternoon, so this is the only time I can do for today, maybe in the evening, but I'm not sure. So let's see. If if not, then then maybe we have to continue tomorrow. So okay, last time we learned the generic data types and how to use traits and how to combine all your code into less code because you can now parameterize everything, which is very good. But then now we have to learn about the lifetime. So lifetimes is another kind of generic. Okay. Initial type and the behavior is not going crazy. So, so yeah, we haven't discussed it in reference and borrowing in chapter 4, and yeah, every reference in Rust has a lifetime. We had that error before in chapter 8 when we tried to do the exercise, which is the scope for which reference is valid. So most of the time, lifetimes are implicit and inferred, but sometimes it does not work. We only must annotate types when multiple types are possible. We have to annotate lifetime when the lifetime of reference could be related in different ways. So when you have a problem, maybe you have to annotate the lifetime. Rust requires us to annotate the relationships using generic lifetime parameters to ensure the actual referenced user runtime would definitely be valid. Annotating lifetime is not even a concept most other programming languages have. We know. Yeah, so lifetime is the main topic here. So, preventing dangling reference with lifetime. So this is the other problem that the opposite of the problem what they had in chapter 8. If something is hanging around for too long, so how do we we prevent them? We have to prevent the dangling references. So so this one had the problem, outer scope, inner scope, because R is in this scope. Oh no, R is in this scope, but the X reference is actually in this lifetime, so R won't work. So it's like the problem we had before, right? We had the commands, the hash map that is sitting outside, but the command is inside the loop, and then we reference something in the command, so that's why it doesn't work. So how do we do that? We can fix it with a different lifetime, isn't it? Outer scope declare variable name R with no initial values, and the inner scope declare a variable name X. Yeah, that's exactly what I said. Inner scope N, we attempt to print the value of R. Because R is referring has gone out of scope, and it's poof, we don't have it. So variable X doesn't live long enough. So that's the same problem we had in chapter 8. So what should we do? How to make it live longer? Extend the lifetime of our reference. There's a borrow checker that compare the scope and see whether it's valid. So we have annotated lifetime for R with A, which is this the whole time here, and then lifetime B. So this is B. So this is A. This is B. Yeah. So B is shorter than A. That's why it doesn't live long enough to see A, the end of A. Yeah. So how do we fix that? So yeah, fix this. Oh, so now we can fix it by like that, right? So okay, now X lives outside. So B would be having a longer lifetime here, because B starting from here, A starting from here, they both live to the end of the main kind of brackets. So what can we do now? But we had a loop, right? Remember that was the loop that was causing the problem. How can we do that? Yeah, it still doesn't fix that problem, this one, because we were using a loop. So let's see what else we can do. Maybe it helped, maybe it doesn't, maybe we just copy it like we did. We will write a function that returns the longer of the two string slices. The function will take two string slices and return a single string slices. After we've implemented the longest function, the code should print the longest string is whatever it is. So this is string 1, string 2. So this one a string. So this one will become a normal string. String 2, this 2, and then we'll print out the result. So it will take two string slices like this. Yeah, we don't want it to take ownership, so it will be a reference. Everything is a reference. Yeah. It won't compile, I think. It's because let's see. Oops. Also, it suggested that we can specify the lifetime. So here this is referring to this, and then this one. But why? Because like it is interesting. The return type return a generic lifetime parameters on it, because can't tell whether the reference being returned refers to X or Y. I see. Yeah, because it doesn't know whether it returned X or Y, and also doesn't know the scope of X and Y. So here it seems like, oh, they will both live till the end, but what if they don't, right? What if it's something else? So we need to have a yeah, if block is body return So how can we specify it? Maybe it's just like this, as suggested. So let's see. Lifetime annotating syntax. So lifetime annotation won't change how long of the reference live. Rather, they will describe the relationship of the lifetimes of a multiple reference. So this is, it won't extend the lifetime of a variable, but it will annotate it. Reference with a specific lifetime, multiple reference with specific, so it's like -a like that. For the first lifetime, so it's like -a for the first one and -b, -c, I guess. Not dash, sorry, apostrophe a for first one, apostrophe b, apostrophe c. After the %. So that's how we do that. Lifetime annotation is function signatures. we have to declare the generic lifetime parameter inside the brackets between the function name and the parameter list. So because it could be anything, it's generic kind of thing, so we have to put it here, but then we put the ampersand, put the apostrophe a after the ampersand. So it's just like that, and then it will compile, but then like for some lifetime a function take two parameters, both of which are string size that at least live as long as lifetime a. The function signature also tells us that the string size returned the function will live at least as long as lifetime a. So I guess the compiler will calculate what is a. That is the minimal against the 3 or 3. We do not change the lifetime of any values passed in or returned. Rather, we are specifying that the borrowing checker should reject any results that don't adhere to these constraints. The longest function doesn't need to know exactly how long x and y live. Yeah, so they just need to be in the same scope. Some scope can be substituted for a if it fulfills everything. And annotating lifetime in functions, the annotation goes in the function signature, not in the function body. The lifetime annotation becomes part of the contract of the function, just like the type. Yep, having function signature contains the lifetime contract means that analyze the Rust compiler can be simpler. There's a problem with the way a function is annotated or the way it's called. The compiler error can point to the part of your code and the constraint more precisely. If instead Rust compiler made more reference about what we intend the relationship of the lifetime to be, the compiler may only be able to point a use of our code. So instead of something happening within the function, it just annotated at the beginning of the function. So if something went wrong, then we know it's the contract instead of playing hide and seek in all your code that you write. So here now, if we do that, then I think it won't compile, and then it was, instead of saying that it doesn't live long enough, it would just say like, oh, this is not a or something like that. So string 1 is, so yeah, this one will work because if when I use result, it's actually, this is scope A, right? Then A is here. Then string 2 lives like flow A, yes. String 1 lives flow A, yes, so it's fine. This one is fine. This one will compile. But this one won't. This one have a crap here. But this one will not compile. If we put it outside, then this is A. But string 2 is shorter than A, so it doesn't work. Get this error. Borrow does not live long enough, and then borrow is used here. So yeah, so result is valid, but it's because string 2 doesn't live long enough. Because we have annotated it as A. As human, we can look at this code and see the string 1 is longer. String 2, therefore result will contain reference to string 1. So it's probably be okay, but then the compiler can't see the references valid in this case. Yeah, so for human, we kind of see, oh yeah, it should be fine, right? But then, yeah, result is here, but then like result is used here. So yeah, string 1 is the result, and it should be here, it should be okay, right? But no, because the compiler doesn't know whether string 1 will, so technically the compiler can't see this for now. And they could also change to something like just with 1 character or something, then it won't be string 1, it will be string 2. Compiler can see the reference, yes. So, so the borrow checker will check that like this one is allowed. Am I frozen or not? I don't know. So it will see that this one is allowed, but this one is not, because this is out of scope A, which is here. The minimal of the 3 is here, so this is A, and this is not A, so it's not good. Thinking in terms of lifetime. Specify a lifetime parameter depends on what your function is doing. For example, if we change the implementation of longest function to always return the first parameter rather than the longest string slice, then we wouldn't have to specify for lifetime. And the code will compile. So this is not doing the longest, it's just return the first one no matter what. But then the second one doesn't matter, right? Because it always return the first one. Then it will still compile. It doesn't matter if string 2 is out of scope, because it doesn't need to. It may have a runtime error when we try to do that. No, it's actually, it won't have a runtime error, because always return the first one, right? As long as the first one is valid, it's fine. The second one doesn't matter. Does it have any relationship with the lifetime of x or any return values? When returning a reference from a function, the lifetime parameter for the return type needs to match the lifetime parameter for the first for the one of the parameters. So you can say this is like b or something, but like this can be a or b, so you need to match at least one of them. It can't be c and d and then this is a, then it's not, because it's not related. But then like, why are you doing it? Does not refer, for example, like this, right? So it must refer to one of the value created within the scope, otherwise this will be a dangling reference, because the value will go out of scope at the end of the function. This one compile because result is inside, and then you return result, which is like it will die when you when you return it. Owned by current function, no, so it won't compile. Dangling reference is broken, so it won't work. There's no way it's gonna work. So in that case, the best fix would be to return an owned data type rather than a reference. So calling function is then responsible for cleaning up the value. Yeah, so like we did before, right? We make the copy or something, so it's like it will own it. So instead of reference, we just pass maybe a string, so that like it will change the ownership. Right. So lifetime syntax is about connecting the lifetime. Yeah, so it's like, again, it's memory safe. We can't point a reference to something that doesn't exist. for example, like this one, it's a reference to something that we got clear up. So technically we don't own it anymore. So it could be anything else that we don't own. So that would violate the memory safety. Lifetime annotation in a struct. So in a struct, we do something similar like that. So what does it mean? So we create a struct. Important except we have a string, and then so this is just input, and then we create I, which is this struct. It's first sentence. So part that holds a string slice, which is a reference. So I guess it's the same thing, that like because part is holding a reference, then we can say the struct need to be in the same scope. Can't outlive the reference it holds. Yeah. Lifetime elision. Every reference have a lifetime, and you need to specify the lifetime parameter for the function or struct that use reference. However, that compile without a lifetime annotation. What's going on? Okay, so first word, we have this and bytes. So we return the slice and S, and S is probably coming from here. Wait. S is creating S is creating input. So it needs to live as long as the input, right? Compile with a lifetime annotation is historical. What? Early versions, this code would have compiled because every reference needs an explicit lifetime at that time. The section would have been written like this. So this is what it would have looked like. Yeah, because like I said, this needs to be living as long as this, right? So it's A, and then this probably is A as well. So this is like no good explanation. It's just because historical reason. That's why, because of reasons. Pre 1.0, that's a long time. Yeah. Entering the same lifetime annotation over and over in particular situations. It's predictable, and so the broad checker would infer lifetime in situation and wouldn't need explicit annotations. So for example, this one, the compiler will handle it for you. You know, if input and output should have the same lifetime, probably everything should have the same lifetime. The patterns programmed into Rust analyst of reference are called lifetime elision rules. These are rules for programmers to follow. They are such a particular case that the compiler will consider. So there are already some rules that have some like preset there that you don't have to explicitly do the like that annotate everything. If your code fit these cases, then you don't have to write it explicitly. It's a shortcut, I guess. The elision rules don't provide full inference. If Rust deterministically apply the rules, but there's still ambiguity as to what lifetime the reference have, the compiler won't guess, and you just shout at your face, and then you have to fix it. Give you an error. So there are some rules that the compiler will just like use those rules to assume things, but if anything that doesn't fit into those rules, then yeah, you will get shouted at and you have to fix it explicitly yourself. Lifetime on a function or method parameters are called input lifetime, and input lifetimes on return values are called output lifetimes. Compiler uses 3 rules to figure out the lifetimes. When there isn't explicit annotations, first rule is the input lifetime. Second and third rule apply to output lifetimes. If a compiler gets to the end of the 3 rules and there are still references for which it can't figure it out, then it will give you the error and set phase. This rule apply to function definition, also input box. So first rule is that the compiler will assign a lifetime parameter to each parameter that's a reference. In other words, a function with one parameter gets a lifetime parameter. So for example, in that case, we have only one parameter. So assuming the input and the function will have the same lifetime. Function with 2 parameters get 2 separate lifetimes. So if you got 2, then it's 2. Okay. So the second rule is that if there's explicit exactly one output lifetime parameter, then the lifetime is assigned to all output lifetime parameters. I think this one fits into this rule because there's only one input and it's so it's assigned to the output and it matches, right? So if there's more than one output, then you got A and B, so you got different ones. Yeah, so if it's one input, then you can just assign the same as output. You can just assume that. Third rule, there are multiple inputs, but one of them is self or mu self. Because it's a method, then the lifetime of self is assigned to all output lifetime parameters. So yeah, it kind of makes sense because all output live as long as self. It will be weird if self got destroyed and then you still have an output hanging somewhere. Make method much nicer to read and write because fewer symbols are necessary. Let's pretend we're at the compiler. So this one, it works because we only got one parameter. Only got one parameter, so that's the one lifetime there, A, and then we apply it to this, and then it works. So it works. Look at another example. If we have longest, then we have A and B, right? And then you assign A to this, but then it doesn't work because if you always return the first one, it will work. Oh no, it won't because yeah, you still have to explicitly because it doesn't know A or B, right? So it doesn't work like that. The second rule doesn't apply because there's more than one input. So basically, anything with more than one input, you have to explicitly state that. Yeah, after working through the 3 rules, still haven't figured out what the return type lifetime is. That's why we got an error. But still couldn't figure out the lifetime. Yeah. The third will only apply in method signature, so yeah, it doesn't apply here. Lifetime annotation in method definitions. So it's the same. We have impel, so we also apply there. Reference may have tied to lifetime of reference in the struct field. They may be independent. So it needs to be declared because we don't know what it wants to depend on. Hello. Hello. Yes, I'm learning Rust. Yes. So yeah, like we have the. So now we have the input block, but we have to explicitly label it because we can't infer them, right? Like it could be related to anything, so we don't know. struct name, because yeah, the struct will have this if you already like declare lifetime of struct, but it could be like, so it could be the same like this, like tied to the lifetime of the struct, or could be independent, could be about something else, like maybe about the input parameter, whatever. So lifetime erosion rules often make it so that lifetime annotation are necessary in method signatures. So for example here, so it's not referencing to anything, so it's just in integer, so it's fine. The lifetime parameter declaration after impel and its use after the type name are required, but we are not required to annotate the lifetime of the reference to self, because the first erosion rule, so you know, it's fine, this could be the lifetime of self, but because this doesn't have a lifetime, so it's fine. So if we have something returned that has a specific lifetime, then we can apply the third rule. For example, here we have self, announcement, and then this. So there are two inputs. So Rust will apply the first lifetime. So this will be A, this will be B. Or if you don't want to copy this, as I C a D, let's say. So because it's n self, so this will be C if this is C and D. So yeah. Special lifetime we need to discuss is static. Yeah, and which denotes the affected reference can live for the entire duration of the program. Woo! All string literals have the static lifetime, which we can annotate as follow. Can we fix our problem before with static? I think it's a bad practice, but we could technically do that. Text of this string is stored directly in the program's binary. Therefore, the lifetime of all string literals is static. You may see suggestion to use static lifetime in error message, but before specifying static as a lifetime of reference, think about whether the reference you have actually lives the entire lifetime of your program or not. Yeah, so wicked magic here applies. So don't do crazy things like, you know, like making everything static, yes, but no, you'll waste a lot of memory if you don't need them. They are like there forever. Most of the time, the error message suggests the static lifetime result from attempt to create a dangling reference or a mismatch of available lifetimes. Fix those problems, not to cheat by making everything static. Okay. Generic type parameters. Trait bounds and lifetime together. So why are all these related together? So we can have a look now. So look at the syntax of specific generic type parameters. So all in one function. So longest with an announcement. So here, so what do we have? We have a function, we have a generic type, and we have a lifetime. So the lifetime of the input x and y reference should be the same as the lifetime of what it gave away, and there's a end that is the type t. So where t is that has the display, need to have the display, otherwise it won't work. And also, so what this function does, right? So this is what this function does. So it will print announcement. So end. So end need to have display, right? Otherwise it may not be able to show here. And then if, so it depends on x and y, and then the length, then it will return. So this is kind of ambiguous. That's why we have to annotate this, right? So longest function yeah, so it's just combine the two. It's doing something quite silly here, but you just combine the two so you can like use it together like that. So just to check whether you have remember everything. Yeah, so it's come to the end. I feel a bit low energy right now because like I wake up early to do things, and now it's crawling back to me that I want to sleep. So I haven't really like, I am drinking coffee, but I haven't fully absorbed all the caffeine, so I'm still a bit spinning and tired and stuff. But we have go through chapter 10, so let's read the summary, and then I definitely need a break, and then I have something to do in the afternoon. Maybe I'll come back in the evening. So what have we learned in this chapter? We have learned all these, of course, like generic type traits, this way we're using it, and the annotation of lifetime. But we yeah. But let's read the summary. We cover a lot of this chapter. Yes, I know. Yeah. So that like now we know how to use those without repetition. We can now have and use the lifetime smartly, things like that. So also we know like what happens to the analysis compiler and we'll do the analysis of the lifetime and stuff. There's so much more to learn. Chapter 7 we'll come back to like discuss the trait objects and other things. Also more complex scenario involving more annotation. So we'll always come back to this, I guess. So let's recap. So generic type, that for the function is like this, so we can have a generic type here, and then we can use trait. For example, we can say that all the types that have display, then they would have the same behavior, that they can have this function that have this, so they can be used here as so wait, this is not n type. Wait. But like, how do we use that? Oh yeah, we take it in here. Okay, sorry, I told you I'm tired. So yeah, we also have like t need to be a type that with display, that it can be used here with this generic type function, and then we can also have the annotation here. That I guess we don't define our own trait, we just use the display here, but it's fine. And then we have the lifetime annotation. So so now we know what this is going on here, right? So because we have learned all of these things in chapter 10. So this is the end of chapter 10, and I yes, you can see I'm already like very confused and tired. So I'll end it here for today, and I hope I have time to come back this evening, and I'll feel like I'll be more energized. But I will see. If I don't see you this evening, I'll see you tomorrow. Tomorrow I have more time to do more Rust. So I will see you there. So goodbye for now, and see you.